Good afternoon, all of you.
Good afternoon, sir.
Good afternoon, sir.
I am audible to you.
Yes, sir.
Yes,
Can
sir.
you see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
So today we will discuss solar cell and its applications. In previous class, we have finished the PN junction, the basic. Now today we will start solar cell and its application. A solar cell basically a PN junction device which converts incident solar radiation into electrical energy, right? Electrical energy means in solar cell what will happen when it is illuminated by sunlight, then in the junction region electron hole pair creation will take place and they will separated by the electric field at the junction and they will carry current and that current will charge up a battery, that is the load. Then it can store this energy, it can be used for later time. So this is the basic of conversion of energy, solar energy to electrical energy and store it. Now the fundamental things that to convert it, what is the solar radiation, what is its wavelength, it is coming, then what type of material we need for solar cell, that we will discuss. The source of solar energy is the nuclear fission reaction. In every second, about 6 into 10 to the power 11 kg of hydrogen is converted into helium with a mass loss of 4 into 10 to the power 3 kg. This mass loss can be converted into 4 into 10 to the power 20 joule energy according to Einstein relation equal to mc.
Hello. Hello. ఇంకా చూస్తే ఎవరు లేరు లేదనుకో వదిలేసి.
Hello?
Sir,
Hello? Is there any problem? What happened?
Nothing. Sir, you are muted for a while actually.
No, I have not muted. Maybe somebody you are disturbing. Right? Now at present it is okay?
Yes, sir. Yes.
Yes,
yes, sir.
Yes, sir.
Yes, sir.
Okay. So we can continue.
Yeah.
So this solar radiation at the above the earth atmosphere which is marked by this yellow color, and at the sea level it is mentioned by this red color, right? So this is the solar radiation. Now within this range what is available to us, this particular wavelength we can use it, right? And accordingly we have to design the solar cell. Accordingly, we have to design the solar cell to capture this particular wavelength region and convert it into electrical energy. Right? This is needed. Now, one thing I want to mention here, that the intensity of solar radiation outside the Earth atmosphere, this is gives the total power flow through a unit area perpendicular to the direction of the sun, is called the solar constant, or it is called air mass zero. Air mass zero, or the solar constant. That means the intensity of solar radiation outside the Earth atmosphere gives the total power flow through a unit area perpendicular to the direction of the sun, is called the solar constant or air mass zero. And this value is 1367 watt per meter square. 1367 watt per meter square. The air mass is defined as sec phi, where phi is the angle between the vertical and the sun position. Where phi is the angle between the vertical and sun position. Right? The air mass is defined as sec phi, where phi is the angle between the vertical and the sun position. So these are the wavelength energy which are interested. Now we come to the basic principle of solar cell. The PN junction solar cell. In PN junction solar cell, what is happening when it is PN junction is formed? In previous class we have already mentioned that in the depletion region there is a electron and hole movement will take place, and then the region will be electrically positive and negative charge will present, and that charge will produce an electric field. This field inside this junction is responsible for separating the generated electron hole pair, and then this electric field will move the electron towards the n side and hole towards the p side. Right? Suppose in the solar cell, I will go for next figure, that will be better. Hello, here you see in this region the electric field is present and it is illuminated by light, and its energy is h nu. Then what will happen in this region? Electron hole pair creation will take place, and this electric field will separate them, and the electron will come towards this direction and hole will go towards this p side, and then hole will be gathered in the p side and electron will be gathered in this n side. Then if you add this by some wire, then what will happen? Electron will move from n side towards the p side, and then it will neutralize the hole. That means in the external circuit we will get one current from p to n, and in the junction you see electron is moving from p to n and hole is moving from n to p. Right? So in the junction we will get another current, that is IL current. We will call it IL current. And now, for example, when we add these two terminal with some wire that has some resistance, RL. So what will happen? Due to this resistance, this electron will flow from N to P to neutralize the hole at P region, then this current will produce some drop. This current will produce some drop across RL. So when the voltage drop will take place, that will produce some positive biasing or forward biasing. That potential drop across the resistance will produce some forward biasing in the P side with respect to N. And then a current will set up. External current will set up, that is I. So this current, overall this current, that we can say one current is, this is the forward current due to the setup of this voltage V, that is IF, and another current, that is photo generated current, IL, right? IL is the photo generated current. So resultant current will be where? Here. The resultant current will be IF minus IL. One is forward current because this is established due to the resistance RL. With this resistance, some voltage drop will appear. That voltage forward bias the device, and that leads to the overall current in the circuit, that is I. That I will be IF minus IL. IL is the photo generated current, right? And forward bias current, according to diode model, you know, that is IS e to the power EV by KT minus 1 minus IL, right? This is the things in what I have mentioned here, and then it is in mathematical representation. So the current in the circuit is I, that is IF minus IL. IF value you know from your diode equation, that is ISEV, where V is the voltage, forward voltage across the junction, right? That established due to this potential drop across the load, that is e to the power EV by KT minus 1 minus IL, where IS is reverse saturation current, that is A into JS. JS is the current density. And if you consider the IV characteristics for a particular solar cell, then it looks like this. And previously, I have already mentioned that it is in the fourth coordinate, right? When we discuss regarding the PM, I have place in fourth coordinate. So it takes place, but here apparently you can see it is in the first coordinate. Current is positive, voltage is positive. So that means here I have mentioned here, that is the mirror image respect to voltage axis. This representation is the mirror image with respect to voltage axis. That means it is present actually in the fourth coordinate, but I have taken the mirror image of that with respect to the voltage axis, right? And this is the maximum current, this is the maximum voltage, this is the open circuit voltage, and this is the short circuit current. So the expression of current is this. From this current expression, we can calculate the open circuit voltage, short circuit current, all those things. Now we come to those. The short circuit currents occurs, short circuit occurs when RL equal to 0. That means when we add these two terminal simply by a wire having resistance 0. So if the wire has 0 resistance, then it indicates the short circuit. So under that condition, V will be 0. So that V will be 0. Therefore, short circuit current ISC, that is equal to I equal to IL. Short circuit current will be, that is ISC, short circuit, that is equal to IL, that is the photo current. Because this voltage will be zero, resistance will be zero, no voltage will develop, that then we will get the current is IL. So this short circuit current is the maximum current. This is the maximum current that can flow in the junction. This is the short circuit current. That is ISC equal to I equal to I. Next, we consider the open circuit voltage. Open circuit voltage means when RL equal to infinity. That means the load of the circuit is very high, infinite load. In that condition, we consider that the circuit is under open condition. So in open condition, the voltage developed at these two terminal will be the maximum voltage, right? So we consider that open circuit voltage. In this condition, the total current in the circuit is zero. There is no current flow through this circuit, external circuit. Current zero means no current in the external circuit. The voltage across the device will be V equal to VOC, that is the open circuit voltage, which can be calculated by using this. If we put current equal to 0, then this quantity equal to 0. So that means IL divided by IS plus 1. Then if you take log of that, then we calculate V equal to KT by E, K2 by E, ln IL by IS plus 1. So this is the open circuit voltage. So this is open circuit voltage. And power delivered to the load. The power delivered to the load, that is equal to P equal to IV. That is IS e to the power EV divided by KT minus 1 multiplied by V minus ILV. Right? So this is the power delivered in the load. By maximizing this power with respect to current or with respect to voltage, then we can plate the maximum power delivered in the load, and at the same time we can also calculate the maximum current in the load and maximum voltage at the load. So if we draw the short circuit current, if we calculate an open circuit voltage, then if we draw the IV characteristics of solar cell, then we can calculate the maximum power rectangle. That maximum power rectangle we can draw, and then from the voltage and current axis, we can calculate the maximum current and maximum voltage which is delivered to the load. Maximum current and maximum voltage that is delivered to the load. This is known as maximum power rectangle. Right. So taking the differentiation of equation 3, we can calculate the maximum voltage and maximum current by taking differentiation and some numerical mathematical steps. We can calculate the VM, that is maximum voltage at the load. So that maximum voltage is VOC, open circuit voltage, minus KT by E ln 1 plus E VM by KT. Right? So this indicates the maximum voltage, but this VM is also present here. So we can solve it. So it indicates the maximum voltage. And similarly, by differentiating this equation 3, we can calculate again the maximum current, that is equal to IL 1 minus KT by I 1 into 1 minus KT by EVM. So the maximum power will be IMVM, maximum power that we can calculate like this, voltage into current. So if you multiply it, then we will get this expression. We will calculate this expression. So this is PM. After mathematical simplification, after simplification we will get this expression, that is the maximum power in the load. And from this maximum power we can calculate the efficiency, that conversion efficiency of the cell. So conversion efficiency of the cell eta, that is equal to PM divided by P in, maximum power output, maximum output power divided by input. Input, that is the optical energy, that is incident optical energy input, that is P max, that is equal to I max into V max divided by P in. And here we can define another term, FF, that is the fill factor. So fill factor, that is multiplied by IL VOC, and IL, that is the maximum current, that is the IL is the short circuit current. IL means it is the short circuit current, maximum current value, that is FF into IL into VOC divided by P in, where P in is the incident power and FF is the fill factor. And this fill factor can be defined as, this is IMVM equal to, we can write FF into IL VOC, or IL means ISC. So that we can write FF, fill factor, that is IMVM, maximum current, maximum voltage product, divided by IL VOC. So this value we know from this expression. So if you take from equation 6, that is if you take VOC outside this bracket, then we can write here VOC and here EVOC. So this expression we can write here, and where IM VM divided by IL VOC, from equation 6 we can write this. So this is the expression for fill factor. This is the expression for fill factor. Right. Now this is all about for solar cell. We consider here that we have not considered any external resistance, in the solar cell. Only load is there. But if we consider a series resistance, for this series resistance, then what will happen? This current expression of that solar cell, due to the presence of this series resistance or this load resistance, in absence of this we are considering all this derivation. So in presence of that some series resistance, what will happen? It will takes the form of current I equal to Is e to the power EV minus IRS divided by KT. That means when some resistance is present, that will produce some drop. So that drop voltage should be considered into the account. And when we consider it, the resistance, series resistance is present, then it will, the expression of current will be takes this form. And under this, the power delivered to the load will be like this: I KT by E ln IIL divided by IS plus 1 plus IRS. This is the drop in the across the series resistance that can be considered if we consider some series resistance. Now next we consider solar panel, or conversion of solar energy to electrical energy. Now with this the efficiency or the output of a solar cell, of a single solar cell, that is not possible to use or any application, right? For using a simply single solar cell, it is not possible to use it. So for that reason, we need a solar panel. Solar panel, that means it is the connected solar cell, a number of solar cell connected in a internally connected a number of solar cell. That is the solar panel. The power generation using a single solar cell is not adequate for practical application. Solar panel is an interconnected assembly of photovoltaic cell or solar cell, which can be used for conversion of solar energy to electrical energy for practical application in standalone system, or maybe small industry, or maybe household component. And that can be generated, electrical energy can be stored in some storage system, that is battery, and that can be used further. For particular application or in other way, the solar cell are connected in parallel. If we connect the solar cell in parallel to yield a higher current, that will produce high current, or in case of series, then it will produce the voltage. Then in case of series, it will produce high, voltage will be more. But there may be, according to requirement, it may be as well as parallel combination is needed. That's mean array, solar cell array, that is the panel, solar panel, for adequate amount of voltage and current, that can be applicable, right? Adequate amount of voltage and current, that is possible by considering the solar panel, which is a array. In that array, parallel and series combination are present. Now this solar cell can be used for a small calculator, which can consume a power less than milliwatt, or to solar, maybe some solar plant that can be generate of energy of few megawatt, and it is mainly used for different purpose. And beside this, also in satellite, this solar panel is also there to generate the power to running the equipments or instrument which is present in that satellite system. And next, the efficiency, that material semiconductor material having band gap energy 1 eV to 2 eV are useful for solar cell devices. 1 to 2 eV, that is useful for solar cell devices. The efficiency can be 28%, or it can be in case of compound solar cell, that is from compound semiconductor material that can be used, that is gallium indium phosphide or gallium arsenide, or tandem solar cell. In those cases, 30% or more than 30% efficiency can be possible to achieve in case of solar cell, the efficiency. And by this, with this efficiency, by connecting them in a series as well as in parallel combination, right, series and parallel, for adequate amount of voltage and current that can be generated for practical application, right? So this is the things that I want to discuss, and then we come to some problem. I have given 2-3 example here. Problem 1, at room temperature T equal to 300 K, at 300 K, solar cell has short circuit. A typical solar cell has short circuit current of 16 milliampere and open circuit voltage 480 millivolt. Current is 16 milliampere and open circuit voltage is 480 millivolt. When it is illuminated with light of intensity, when it is illuminated by light with intensity 600 watt per meter square. Light of intensity 600 watt per meter square. This is the things. Calculate the short circuit current and open circuit voltage when the light intensity is increased to 1050 watt per meter square. When the light intensity increased to 1050 watt per meter square, then what will be the open circuit voltage and short circuit current that you need to calculate. So open circuit voltage that we have already mentioned, that is kT by E ln IL divided by IS plus 1, that nearly equal to, we can exclude this one, that is IL by IS. Now if we take for two cases of current, I1 and I2, right? I1 and I2, then VOC2 minus VOC1, that will gives you this KT by E ln IL2 by IL1 from this, right? And here we can write, that is ISC, ISC2, ISC1, that is I2, I1. So then ISC2, that you can calculate by this. So this value you know, short circuit current for case 1 you know, so you can calculate the short circuit current in case 2, that is 28 milliampere. And open circuit voltage in case 2, that is the first case, plus this will be add up. So when you add up this, then it is 0.48 volt, and this KT by E, that is 0.2 thermally equivalent voltage at T equal to 300 K, that value is 0.0259, and ln of this quantity, that will gives you 494.5 volt. So under the condition of 1050 watt per meter square, your open circuit voltage is this and short circuit current is this. Point is clear? Next problem is based on fill factor. The expression of fill factor of a particular solar cell is given. Fill factor is VOC minus ln VOC plus 0.72 divided by VOC plus 2. It is given. Fill factor is like this, where VOC is VOC divided by VT, temperature equivalent voltage. VT is the thermal voltage. Calculate the maximum power output at T equal to 250K, 300K and 350K. Given that VOC equal to 0.6 volt and I short circuit equal to 36 milliampere. Right? The value of VOC at T equal to 250K. So if you put T equal to 250K, then what is the value of, what is asking? Calculate the maximum power output. Power output you have to calculate. That is fill factor multiplied by ISC VOC. So the value of VOC at T equal to 250K, that is 0.6 divided by KT by E. So this value, VOC divided by this, so that value is 27.78. So VOC is ato for 300 and 350K. Now fill factor you have to calculate, that is 0.82. For VOC this fill factor is 0.79. For VOC is this, and fill factor is ato for this VOC from this expression we have calculated. Then maximum output power, that is P in, fill factor into short circuit current and open circuit voltage, that value are given. So using this we can calculate the output, maximum output power, like this. So these are the maximum power output. Next, we consider another problem. Problem 3. A particular family uses 5 electric light, each of 40 watt, every day for 6 hours. They also use 2 fans, each of 60 watt every day for 14 hours. The family member use one television, 180 watt for 6 hours per day. The average solar intensity incident per day is 8 kilowatt hour per meter square. 8 kilowatt hour per meter square. And a solar panel converts solar energy to electrical energy, has efficiency of 12%. Calculate the minimum device area. Now you need the solar panel, so that solar panel area you need to calculate under this situation, so that this family can support all his activity from solar panel. So what will be the area of that solar panel? So total power consumption by this family, 3960 watt hour. And the conversion efficiency is 12%, and incident power is 8 into 10 to the power 3 multiplied by conversion efficiency, that is watt hour, multiplied by area, A, watt hour. So this will be equal to this. So these two will be equal. Then after considering the value of A, that is 4.125 meter square. So solar panel should have the area 4.125 meter square, so that, or larger than that, this, then the family can support his all household activity of power from this solar panel, right? So I want to stop it here. This is all about for solar panel, or solar cell and its application. And I will share this note today, so you can download or you can read from this and prepare yourself, right? If you have any queries, any problem, you can send me by email regarding this. If there is any difficulty, then you can send that problem to me by email, right? Otherwise I will not consider this. I will consider that you have, all of you understand, and I have already given the problem. You should practice like this for your examination. So next class we will discuss another things. On every Monday I will continue this class. Every Monday I will continue this class. Okay, so I will stop it here.
Thank you, sir.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.